All right, so like he said, I'm Mark Myler. I'm a principal engineer. I work at Cox Automotive, and I've been tasked to set up the companies and build and operate our federation layer. So thanks everybody for coming. Welcome to Better Together, how Cox Automotive secures their graph with Apollo and Kong. So I'm going to start with a quick introduction of who Cox Auto is. You know, we're an automotive software company, and we want to transform the way the world buys, sells, owns, and uses vehicles. Cox is a huge company. We got about 34,000 team members, and in North America, we have over 40,000 dealership partnerships. Cox Automotive consists of several keystone products, which are themselves made of many other products. If you have bought a used car in the past 20 years, I can guarantee you that my company had some fingers in the transaction of that vehicle's sale. But Cox is currently undergoing a lot of growing pains. Many of our solutions were acquired in business mergers. I myself became a Cox employee through such an acquisition. So in addition to that, Cox has a long tradition of you build it, you run it, which allows teams a lot of flexibility to execute quickly, but it also means our solutions are very diverse. What this all boils down to is that our data and functionality are spread out across the entire enterprise, and they're also in lots of different hosted cloud provider accounts and data centers. Now, for this audience, in this conference, you know, we all know how powerful Apollo Federation is, and so we all know that that's going to solve a lot of these problems. But there's some challenges of using Federation when your subgraphs are so highly distributed. So as we built out our federation layer here at Cox, there were some critical questions that popped up that we needed to answer. The first question, you know, how should we manage networking between the federation layer and our subgraphs? Having to create network paths to subgraphs with tools like VPC peering and direct connect are time-consuming, both for initial setup and maintenance. And my team is small, and I don't want to spend a whole lot of time on network engineering. Furthermore, such rigid network connections can also make disaster recovery situations difficult. The next question, how are we going to manage authentication and authorization? You know, this is a shared problem for all of our subgraphs. I don't want each team to build out their own methods for doing this. Now, using an identity provider seems like an obvious solution here, but a follow-up question to that would be, how difficult is it for customers to manage all of their scopes in a federated world? And the last question, how should we secure communication between the federation layer and our subgraphs? Is there a level of trust between the two of them, or do we need to build a special auth process? So the solution to all these questions is, let's use an API gateway. Well, what is an API gateway? Gateway should be a point of entry into your a single point of entry into your network, and act as an intermediary between client applications and your upstream services. Now, this point can't be overstated enough. All inbound traffic must come through your gateway. A single point of entry minimizes potential attack surfaces and allows us to focus all of our security efforts on this one point. A single point of entry also allows us to solve a lot of shared problems that our upstream services has. So why should each service write its own code for something that I can do for them? Gateways are also responsible for user authentication, whether through an API key or a JSON web token. And gateways are also responsible for authorization, either through access control list, OAuth scopes, or integration with some sort of policy management tool. All the above points mean that an API gateway can act as a trust boundary for your internal network. When your upstream applications receive a request from your gateway, they can trust that it's a legitimate request that has already been authenticated and authorized. Next up, upstream services need to be protected from request floods, so gateways need to provide rate limiting. And then any respectable gateway will have built-in telemetry tools, so you know who's making what request and to what services. And being the point of entry, they are also an excellent place to start your distributed traces. And then last up, this one's not a hard requirement, but any gateway is also going to give you the ability to write custom code to add functionality as required by your business needs. Okay, so given all that, you're probably asking, well, isn't the Apollo router a gateway? So let's do a quick, and let's find out. The very design of Federation requires that the router be an intermediary and a single point of entry. It just wouldn't work otherwise. Combined with an identity provider, the Apollo router has extremely good authentication and authorization out of the box with JWT validation support and at-required scopes and at-policy schema declaratives. So check marks for the first two mean that the Apollo router does satisfy my requirements for being a trust boundary. The router has basic rate limiting, which it does so globally for all requests. You can't filter it for consumers or IPs. But however, as an alternative, it does have operation limits and demand control to help protect upstreams. So it's kind of in the same spirit as rate limits, so we'll give it this one too. All right, and the Apollo router also has very good telemetry suite at your disposal. It generates logs, traces, and operation history in GraphOS. Lastly, Apollo lets you customize to your heart's content with RISE scripts, coprocessors, or native Rust plugins. And I especially enjoy the native Rust plugins because, who doesn't like Rust, right? Like, it's a beautiful language. All right, so we're 6 for 6. So based upon my criteria, yeah, it's a gateway. So you can use it one if you want to. But, with all things in tech, everybody has additional use cases that systems need to satisfy. And so here's some of the ones that Cox needed in addition to what we just talked about. Okay, so first of all, I need rate limits to be filtered to individual users. And I also need to be able to enforce different rate limits to one subgraph versus another. This is because Cox's subgraphs have different levels of business investment and performance requirements. Now next, I absolutely love Apollo's client awareness feature. It makes the data in GraphOS a million times more valuable. But, I'm a platform engineer, I have trust issues, and I don't trust my users are going to send me the correct header. So I'm going to set it for them. It's just one less thing for them to send, and in the very rare cases of abuse, I can overwrite it and set the right one. And then I also need fine-grained permissions above and beyond what is supported by my company's identity provider. I want the ability to make it easy for customers to make cross-subgraph queries without also having to have deep, arcane knowledge of each subgraph's scope requirements. I want to authorize them appropriately, regardless of what scopes they will inevitably forget to ask for when they request their token. In addition to that, I also need whatever solution I put in place for this to be performant. I cannot afford to add any latency by using coprocessors to do additional policy management. And then lastly, for reasons that I'll explain later, I also need a way to inject my own authentication headers between the federation layer and subgraphs. Okay, so to meet all these additional use cases, my teams at Cox Auto has decided that the open source version of Kong is going to meet all our needs and will work really well together with the Apollo router. All right, so why Kong? The API gateway market space is pretty saturated these days. There's dozens and dozens and dozens of these products out there. So picking one to complement Apollo is no easy task. Cox Automotive already has its own opinion on the subject by recommending AWS API Gateway. So because I want to use something different, I have to defend my decision with strong data, and so that's exactly what I did. All right, so Kong is already known for its high performance, but I had to test it out for myself, and my testing shows that it is extremely fast. We're talking about no more than about 4 milliseconds of extra latency added to a request with rate limiting, and that's for about 95% of the request. It's even faster without rate limiting. For comparison, AWS API Gateway adds roughly an extra 9 milliseconds instead. In terms of cost, Kong is mind-blowingly affordable. When most API gateways want $1 or more per million requests, like AWS's 2 to 3, anything less than $1 is awesome, and I'm spending 77 cents per million requests. Even better than that, that includes all the infrastructure necessary to hit my resiliency targets. Now, Kong's list of gateway features is backed up by a very extensive library of plugins. They include multiple auth-in methods, access control lists, rate limits, telemetry, and many, many more. So there's a lot of things that this gateway can do for you. And if Kong doesn't have a feature that you want, you can make one yourself. Kong supports custom Lua plugins. And so, at long last, all those years I wasted writing World of Warcraft plugins is paying off here. So Kong is also easy to maintain and configure. It has very safe version migrations, and configuration of services and consumers is made easily through a lot of configuration as code patterns, and we specifically use a Terraform provider owned and operated by Philips Labs. Okay, so if everything I just talked about hasn't convinced you that this is a good idea, I'm going to make one appeal to authority. This isn't just my idea. Kong and Apollo recommend this as well. Around last year's Graph Summit, Apollo and Kong released a joint white paper called Leveraging GraphQL for Next-Gen API Platforms. It's a bit of a read. It put me to sleep several times, but it's a wonderful design and can mostly be summed up in this image here. But the design does make some assumptions that you're using a lot of Kong paid enterprise features, and it does also assume that Kong, your Apollo router, and your subgraphs all exist in a single networking. So Cox, we had to make some adjustments to this. All right, now it's time for the really fun stuff. We're all engineers. This is going to be great. Let's talk about the nitty-gritty details of actually how Cox uses Apollo and Kong together. All right, so I present to you my high-level architecture of the system. So the key system is that in this account, we have Kong and Apollo. That's run by me. And then in any number of other cloud accounts, cloud providers, data centers, on-prem, are our subgraphs, and those are owned by the subgraph teams. We've opted out of using tools like AWS Direct Connect or VPC peering, so subgraph queries will leave the safety of my VPC and spend some time in the public internet. So this is going to make security between the two of them my primary concern. And despite that, I still want to have my cake and eat it too, and I want to leverage my federation layer as a gateway so it can do all the cool gateway things that I've been talking about. Of equal importance is the need to respond to subgraph disasters and fail over appropriately when they have outages. So I have a 99.95% uptime objective for the federation layer, and I accomplish this with a robust multi-region active-active design made possible through Apollo's uplink and Amazon Aurora global databases for Kong. And as a side note, if you use Kong's enterprise feature, that database isn't necessary. You're going to use another product called Kong Connect instead, and it behaves the same way that Apollo Uplink does. So the services in the federation layer run in Docker containers on ECS Fargate and use standard auto-scaling features, so we always have the right amount of capacity at the right time, at the right cost. All right, so now that you know that my subgraph queries leave my federation layer and shot head first into the horrors of the public internet, let's talk about trust boundaries. So here, there's two pretty obvious no trust areas, both located in the wild, and two high trust areas, one in the federation layer after JWT validation, and the other is inside the subgraph network. As stated before, I want to be able to use the federation layer as a gateway, but the break in trust makes that goal questionable. Now, I've seen similar designs push JWT validation all the way into the subgraph, but that negates any of the value that I'm trying to add by having a gateway. Instead, our solution is to build a second authentication method between the federation layer and our subgraphs. So we're going to let the federation layer validate the JWT, authenticate the user, authorize the request, and then we're going to wrap it all up in a new request with a new security token, which we send to the subgraph to say, hey, this is coming from me, you can trust this. We're effectively changing the security question the subgraphs ask from who are you, do you have access, to just, is this request coming from the federation layer? All right, to better understand the overall design, Let's go ahead and walk through the entire life cycle of a request, starting with ingress. All right. Step one is routing the request from the user to one of our AWS regions. This is done with standard implementation of AWS Route 53 latency-based routing, monitored by Route 53 health checks for automatic failover. Now, important detail with this is that because the federation layer consists of two services, I can't just point the health check at the Apollo router and call it done. Instead, I have a Kong service that will proxy the request to the Apollo router. So that health check goes through the whole system. If either one of them's down, we're going to fail over. Step two is protecting ourselves with a web application firewall. Now, I've heard horror stories before about how firewalls and GraphQL don't play well together, and this hasn't been the case at Cox Automotive. We're following AWS best practices by using AWS managed rules. And I'm not going to iterate over the entire list, that would be boring. But if you're interested, just Google AWS managed rules rule group list, and you'll find all the rules that we're successfully using. In the rare instances that if one of these rules did cause problems with us, we are not going to create custom rules to get around the managed rules. We have a relationship with our AWS technical account manager, and we would work with them directly to fix the rule. No custom rules. That's kind of important because I feel like people creating custom rules, that's where you get into trouble. Next, ingress is also protected from distributed denial of service attacks with the aid of AWS Shield. And we've also enrolled in proactive engagement. And that means that the Shield response team will actively monitor our services and contact us if there's an event. And they also have an automatic mitigation feature that we've enabled that, in theory, means I'm not going to have to get out of bed if there's a problem. And so the final step of ingress is that the request is being made is to validate that the request is being made by a legitimate customer. I rely on an enterprise managed OAuth 2 identity provider using the client credentials flow for authentication, not authorization. Kong Enterprise supports integration with your identity provider. The open source version does not. So instead, we maintain our own custom JWT validation plugin from another open source community project. All right, ingress is done. The request is now in our first trust boundary. So in the federation layer, can do all the awesome gateway stuff that we've been talking about. So with the user's JWT now being validated, the next thing the gateway must do is match the request to a Kong consumer. And we do this by mapping a user's ID claim from their JWT to a Kong consumer's custom ID field. And that's a simple, unique string that Kong has created for mappings just for this purpose. And then we have a simple cron process that will automatically sync the user's IDs and descriptions from our identity provider to Kong, so it's completely seamless to our users. All right, and now that we've matched to a Kong consumer, we're going to start enforcing rate limits on a per consumer basis with Kong's rate limit plugin. So now we're going to put into motion the first steps of our authorization process by adding a header containing a list of all the access groups and permissions that a particular consumer has been granted. We do this with Kong's ACL plugin. Note, we're not doing authorization yet. We're going to get to that. But for now, we're simply using Kong as our policy store. Of key importance is that the Kong performs that step in microseconds. Kong also adds some extra headers that identify the consumer so that Subgrass can apply user-specific business logic if necessary. And this is also where I set the Apollo client awareness header automatically for the user so that every trace and metric and GraphOS has the appropriate and correct mapping. And then lastly, as mentioned before, Gateway is an excellent place to do distributed tracing, and so I do that with Kong's ZipKit plugin, which works with OpenTelemetry. Okay, so from here, Kong will proxy the request to the Apollo router. In addition to all the awesome things we know that the router does for federation, this is where I do authorization. I begin by doing a redundant JWT validation with Apollo router's built-in JWT functionality. It's practically free from a performance standpoint, and this is necessary for using the @required scope schema declarative if you want to. However, I would rather use the @policy schema declarative for authorization. And I do this through a custom RISE script, which will inject all the Kong access groups we talked about in the last slide into the policy context used by the Apollo router. And so here's that RISE script. 9 lines of code to take Kong's access groups and add them to a context that the Apollo router can use to make authorization decisions. No cost to coprocessors, no custom binaries with native Rust plugins, just 9 lines of code to take Kong's ex-consumer groups header and map them to the policies required by the query being made. From here, the router will take over and approve or deny authorization. This is all done quickly, behind the scenes for the user, and this solves the concerns about the users having to know what scopes they need access to access any given subgraph or field. With this, we can now create schemas like this that have multiple authorization requirements, but the user isn't responsible for knowing any of this when they ask for their JWT. Any valid JWT will do. This eliminates a lot of customer confusion and frustration when it comes to navigating subgraphs. All right, so normally, at this point, the Apollo router is going to decompose the query into the necessary number of subqueries and send them back to the correct subgraphs. But instead of sending them directly to a subgraph, I'm going to send them back to Kong, which manages that subgraph's routing URL. This is probably the biggest deviation from the Apollo Kong white paper. While it's going to recommend the use of a service mesh like Kong Mesh, I reuse Kong Gateway instead, because Kong provides all the features that I need at this part in the life cycle, and I don't really want to use a service mesh. You know, it adds a whole bunch of unnecessary complexity, and it's one less thing that I have to pay for. So a big thing we do here also is that this is where we enforce subgraph-specific rate limits that we've been talking about. Each subgraph can have its own default rate limit, but then individual consumers can be granted additional limits for specific subgraphs as needed. Now, most importantly, here is where the authentication lifecycle between the federation layer and subgraphs begins, and I do this by adding a new auth header and an appropriate token secret known only to the federation layer and the subgraph. Okay, so the federation layer is done now, and it's time to proxy each subquery request to the appropriate subgraphs. You know, first up is egress to the public internet, and this is done through my NAT gateway. These have static IP addresses known only to me and my subgraphs, and we're going to come back to that detail in 1 second. Next, routing to subgraphs is then done by using DNS records that are fully owned and maintained by the subgraph teams, not me. This is critical for the fastest possible recovery times if a subgraph has an outage. With this strategy, the federation layer basically doesn't do anything. It just respects the DNS records. This allows subgraphs to have their own resiliency targets and failover procedures based upon their own needs. Now, our subgraph teams are encouraged to use similar multi-region strategies as the federation layer, but subgraphs may just not be business critical enough to justify the investment. So this all makes a flexible, highly available system, and as a bonus, I'm not getting out of bed to help people when they have problems. Next up, we have ingress into a subgraph's network. So all of my subgraphs, regardless of data center, cloud provider, or wherever they may be, they have to have a firewall. So we're going to leverage these in 2 additional ways. So those IPs from my NAT gateway, which we've talked about, those are going to be added to the IP allow list. And so if a request comes from anywhere else, we're going to deny it. And that's an okay security measure. You know, we all know IPs can be spoofed. So we're going to have to do something a little bit more. And that's where that authentication header that we've been talking about comes in. Our subgraphs make sure that that header is there. They make sure the value is there, and it matches the secrets that we agreed upon. Okay, so I'm a platform engineer. I'm not a cybersecurity guy. So this part makes me a little nervous. And I actually engaged with Cox's cybersecurity team, and they did a whole audit on this thing. And they spent a lot of time poking and prodding at it. And after about 4 weeks, they came back and said, hey, you're approved to use this. This is your stamp of approval. So we're moving forward with this. Okay, and now we're inside our secondary trust boundary. Subgraphs know that the requests are coming from the federation layer, and they can trust that the original request has been authenticated and authorized. Using the consumer identity headers added by Kong and combined with the ACL headers, a subgraph can also run any business logic it needs for user-specific business logic. The primary use case here is for row-based authorization, because I might have, for example, I might have one customer who's paying for US vehicle valuations, but they're not paying for Canadian vehicle valuations. And so with those headers, they'll be able to say, you only have US, and they'll delete all the Canadian stuff from the response. All right. So you're probably all thinking, about all the many network hops my federation layer is making at this point, right? This is some type of gateway inception. It's gateways all the way down. The natural question is, or the natural reaction is, this can't possibly be fast. But yes, it is fast. In fact, it's really fast. Remember, I talked about how Kong was fast with 4 milliseconds added. But the Apollo router, which I haven't talked about, is even faster. And I've done load tests that show that for basic operations, not massive, huge, complex queries that go everywhere, but it will at most add 2 milliseconds of latency. So what we're looking at here is Kong adds 4 milliseconds, the router adds 2, Kong adds 4 more, and so I can support a 10 millisecond SLA for the federation layer of latency added. So just one other thing to prove how fast this is. I have a revenue critical subgraph with a 50 millisecond SLA. If that SLA ever gets broken, they have a circuit breaker, and then the revenues that application produces is completely gone. And I can't break that by adding too much latency myself. And as long as I've been running this setup in production, I have never once violated my SLA or caused that team to violate its SLA. All right, so Cox has had a lot of success this past year with this design. It's fast, flexible, resilient, and it has a lot of features. And so if you want to know more, why don't you check out that white paper. Again, it's called Leveraging GraphQL for Next-Gen API Platforms, or go ahead and check out the open source Kong and find out for yourself why Kong and Apollo are better together. Thank you.